In this video here, we're going to take a look at locating roots. Now, sometimes we may have equations that can't be solved analytically, and in this case here, we must use numerical methods. So a useful starting point for solving equations like this is being able to locate the roots. Let's say we have a function f of x. We have a function here f of x, and f of x here is continuous on the interval ab. So let me just write this down here. So continuous on the interval AB. So let's just write this down in full. So that's the interval there, AB. Now, if f of A and f of B have different signs, so if f of A and f of B have different signs, or opposite signs we should say really. If they have opposite signs, and in this case here, f of x must have at least one root. So f of x must have at least one root. Must have at least one root. In this case, I'm going to call this root x, but another common letter to use here is the Greek letter alpha. Okay, and you'll see that quite often in questions. Like I said, I'm using x here, but alpha is also very common. So f of x must have at least one root here, x, which satisfies the following inequality. This satisfies x being between a and b. Okay. Now, one thing to mention here before we kind of take a look at any diagrams here is this definition of a continuous function. So just remember, a function is continuous if it does not jump from one value to another. Okay. So let's just take a look now at some diagrams here. So these won't be perfect, but just so we can kind of sketch and illustrate these ideas. Let's say this is my y-axis here. My x-axis here. Okay. Let me just sketch some kind of cubic polynomial here. Okay, so just extend this a little bit. Let's say we've got a cubic polynomial here. Something that looks, say, like this. Okay. Now, clearly here, I would have three roots. I've got this root here, and this root here. Okay. Now, let's say we have this root here. Okay. Obviously, solving this cubic polynomial, nothing too challenging, but just so we can illustrate the idea here. So let me just kind of illustrate these roots. Let's do it in blue here. I've got this root here, this root here. I'm not sure blue's a good color. Let me try and pick a slightly brighter color. Let's use yellow. So I've got this root here, and this root here, and this root here. Okay. So with these three roots here, what I can do is pick, say, a value to the left and to the right here. So if we look at, say, this root here, so let's just say we're between 1 here and 2. Okay. This is 1 here to the left and 2 here to the right. So if I pick f of 1 here, so I've got my function here, y equals f of x, my cubic polynomial or cubic function. So now if we take f of 1 here, so f of 1 here, we notice we get this point here. Okay, and this is positive. So f of 1 here is greater than 0. It's above the x-axis. So hopefully, again, that should sound quite obvious, quite intuitive. Then in this case here, f of 2, that's now going to be less than 0. So it's now below the x-axis here. Okay, so we've got this point here. What this indicates here then is we now have a change of sign. Okay, because we've got this change of sign here. I've got this cubic polynomial which is continuous. There's no gaps, no jumps between any points here on my function. So f of x here is continuous. F of x is continuous. And we have, let me just write this down, and we have sign change between x equals 1 and x equals 2. What this tells us here then is we have a root between 1 and 2. And again, I think from the diagram that sounds, quite obvious. It's clear to see that we have a root here between 1 and 2. Okay, just looking at the diagram, we've got that root there, but using the sign change there, it allows us to locate roots for more complicated functions. Okay, so there's also some things to consider here. Okay, so things to consider. What do we need to consider here? Well, the first thing to consider here is if we have too wide of an interval. So too wide of an interval here, let's just make a note of this. Too wide of an interval. So this is really common with quadratics. So let me just sketch a quadratic here. My x-axis here, got my y-axis here. So if I sketch a quadratic here, okay, let's say something like that. So let me just pick 2 points here. Again, my sketch isn't great. We need a little bit more room to do this, but let's say I've got this point here, A. Okay. And let's say I've got this point here just to the right of my curve, let's say B. Okay. Now let's do this in a different color now. Let's use red here. Then where these points meet the curve here, this one would be positive. So in this case, f of A. So f of A here would be greater than 0. Let's just say this is the curve y equals f of x. In this case here, B as well would also be positive. Okay, it's above the x-axis. So f of B is greater than 0 as well. So f of B is also positive. So in this case here, because we don't have the sign change, what that would tell you then is we don't have a root in this interval. But actually that's not true here. We actually have 2 roots in this case. We've got a root here. We also have a root here. Okay. So you do have to be careful with how wide the interval is. In a question, you are always usually given that interval, so you don't need to worry about that, but it is something to consider. And then the other thing to mention here is, like we've already said, continuous functions. So continuous functions. So in this case here, let's just think about the reciprocal function y equals 1 over x. So I'll just sketch it underneath. Okay, so I've got my x-axis here, the y-axis here. So if you were to think about sketching this function here, we'll get something like that in that quadrant, and in this quadrant here, we'll get something like that. So that is y equals 1 over x. Okay, just a quick sketch there. So if you was to think about this here, let's say I've got this point here A, and this point here B. So I've got A and B here, and again, let me just do this in red. If you was to think about these 2 points here, f of A, so f of A, in this case here, is less than 0, it's below the x-axis, and f of B here is greater than 0. Okay, so that's positive. So what that would indicate then is in this interval here, this interval of AB, that would indicate that there is a sign change, or it tells us a sign change, and in that case would indicate a root there. But this isn't true here, because what we actually have now is an asymptote here. Okay, we have an asymptote here at x equals 0. So x equals 0 is an asymptote, and what that means then is this function here, y equals f of x, so f of x equals 1 over x, that is not a continuous function. Okay, we do have that gap, this function jumps here, so in this case this wouldn't be a continuous function, and that would indicate that there isn't actually a root in that interval. Okay, and there we have it. So it's quite a long introduction there to locating roots, quite a lot of information to take in, but do make a note of everything here. All these points are important to consider. Now let's just take a look at a couple of quick practice questions here for locating roots. Starting off with question 1, now we've got the diagram below which shows a sketch of the curve y equals 1 over x plus 1. We can see the diagram here. Now George claims that because there is a change of sign within the interval here of -2, 1, this indicates that there is at least one root within the interval. We need to explain using the diagram why George is incorrect. So we just take a look at the diagram here. We've got a sketch of the curve y equals 1 over x plus 1. We've got these 2 points here of -2 and 1, and they relate to the interval here. I've also got this blue dotted line here, and this blue dotted line is actually an asymptote to this curve here of y equals 1 over x plus 1. So why is George incorrect here? Well, normally what we consider here is the change of sign, and this is what George has done. So in this case here, f of -2, that's below the x-axis, so that's less than 0. F of 1 here, so f of 1, that is greater than 0. That's above the x-axis now. And in this case here, we have now a change of sign. And what that would normally tell us then is there is a root in that interval. Okay? But we have to be slightly careful here. Because for this function that we're working with here, so if I say that y is equal to f of x here, okay, in this case here, my function is not continuous. We have this jump here, okay, so basically, if you see a vertical asymptote like this, your function is not continuous, okay, so we just explain why George is incorrect here. George is incorrect because our function is not continuous. Might run out of room here, not continuous. About there. So it's quite a quick answer there. George is incorrect because our function is not continuous, but that's simply all we need there. He is correct in that there is a change of sign within the interval. But that's not incorrect. And normally, like we said, that would indicate then that there is at least one root within that interval. But in this case here, this function is not continuous. We have that jump there. Obviously indicated as well by this vertical asymptote. So in that case here, George is incorrect. Okay, and that's all we simply need to say there, giving us a solution to question 1. And finally then, if we take a look here at the very last question, question 2, we've got the diagram below which shows a sketch of the curves y equals 4 minus 2x and y equals the square root of x. We can see the diagram here. So for the first part, part A, we're asked to explain how the diagram shows that the equation for the square root of x equal to 4 minus 2x only has one real solution. What we need to consider here is the points of intersection. So the square root of x equal to 4 minus 2x, in this case here, we're just looking, like we said, for the points of intersection. But in this case here, we only have one point of intersection, that would be here. So all we need to say then is the curves meet at one point. The curves meet at one point. Let's just write this down in full. The curves meet at one point. So in this case here, you can say there is one value of x. There is one value of x that satisfies this equation here, the square root of x being equal to 4 minus 2x. And in this case here then, this shows that there is only one real solution. There is only one real solution. Okay. And there we have it. So that's all we need for the first part there, part A. That's part A done. Let's take a look now at B here. So now we're given that f of x is equal to the square root of x plus 2x minus 4. We're asked to show that the equation f of x equals 0 has a root alpha, where alpha lies between 1 and 2. So f of x here, well, what they've done is they've equated 4 minus 2x and the square root of x together, and then we've obtained this new function here by just rearranging. Okay, let me just write down f of x here. So f of x equal to the square root of x plus 2x minus 4. Okay, so we have a root alpha here where alpha is between 1 and 2. So basically what it's considering here is the point of intersection. And again, from the diagram, this should hopefully seem quite obvious. So my root here, alpha, so in other words, the point of intersection here is between 1 and 2. And you can see that clearly here by considering this interval. Okay, what we're going to do now is show a change of sign. So what we need to consider here is f of 1. So f of 1, so all I'm going to do here now is substitute 1 to my function here for f of x. I'm going to get the square root of 1 plus 2 times 1 minus 4. The square root of 1 is 1, 2 times 1 is 2, minus 4. So here I get 3 minus 4, giving me minus 1 there. Okay, so that's f of 1. What we need to do now is consider f of 2 here. For f of 2 in this case, that would be the square root of 2. We've then got 2x here, so that's 2 times 2. Got 2 times 2, and then we've got minus 4 here. So the square root of 2, leave that as it is. 2 times 2 is 4. And then we've got minus 4 here. So 4 minus 4, that would give us 0. We just get left then with the square root of 2. Okay. So we've got minus 1 here, so that's negative. We then got the square root of 2 here. So what we've got here now is a change of sign. So let me just make a note of this here over to the left. So there is a change of sign. There is a change of sign. And in this case here, this shows us then that there is a root alpha between x equals 1 and x equals 2. So let's just write that down in full. There is a root. In this case here, we've used alpha in this question, so there is a root alpha between x equals 1 and x equals 2. Okay, and there we have it. So that's all we need there for part B. So all we're doing is just showing that change of sign there. So f of 1 is negative, f of 2 is positive. In that case, we've got the change of sign. That means that there must be a root alpha between x equals 1 and x equals 2 there. Okay, and there we have it. So that's the solution to B there. That gives the solution to question 2. And that actually brings the end of this video on locating roots.